Hey there, physics fans. Today I'm going to walk you through an experiment from start to finish where we determine the spring constant for my cart here on the track. We're going to apply conservation of energy, where we take the energy that's stored in a spring and we convert it into kinetic energy of this cart moving. The spring in particular is released by pressing a little button on top of this cart, and we can compress it just by sliding it in. When I have the spring compressed and resting against another object that's not going to move, and I release the spring, all of the energy stored in the spring is converted into kinetic energy in the form of this cart moving down the track. And through conservation of energy, we'll be able to figure out what the spring constant is just by taking a couple of simple measurements. Now, we could do this experiment multiple times under one condition and use statistical averaging to figure out a confidence interval for the spring constant, or we can take advantage of the idea of linearization, where we change one variable and measure a change in a different one. So for this lab, we're going to compress the spring the same distance each time, but as we go through our trials, we'll add additional mass to our cart. And what we'll see over the course of the experiment is that as I add mass, the cart moves slower down the track. And so I'm going to have multiple measurements in the end, and I'll be able to use linearization to improve my experimental results. Before we go any further, I'd like to talk about the assumptions that we need to make in order to conduct this lab. First, we need to make an assumption that our track itself is completely level. If that wasn't the case, then we have to take potential energy due to gravity into account. And depending on how the track was actually oriented, it would either increase the spring constant or decrease it. So I took great care before we started doing this experiment to make it as level as I could. But all the same, it's an assumption that we have to make in order to simplify the math for this experiment. Another assumption that we need to make for this experiment is that the friction is negligible. Certainly you can hear the sound, there is friction present. But ultimately, because we only care about the speed immediately after the spring is released, we shouldn't have to worry about friction, so we can go ahead and neglect that it's going to cause any kind of loss within our measurements. And then finally, we need to make the assumption that we have an ideal spring in our cart. That is required for us to apply Hooke's law and to apply conservation of energy when we're talking about the potential energy stored in the spring. If the spring didn't obey Hooke's law, then we would have some type of error associated with it. And depending on how the spring performed, it could either increase or decrease our determined value of the spring constant. So now, before we go any further, I'd like to turn our attention to the linearization. The first step of our linearization process is to identify the fundamental physics that is going to be used for the conduct of our experiment. And as I discussed already, we're going to apply conservation of energy. That is, the work due to non-conservative forces is equal to the final energy minus the initial energy. And we're assuming that since there's no friction present in our system, that the work due to non-conservative forces is going to be equal to 0. We're going to say that all of our energy in the initial state is stored in the potential energy in the spring, and that all of the energy in the final state is in the form of the kinetic energy with the cart moving. Now, certainly this is a topic that'll be covered throughout Physics 1, so I'm going to go ahead and jump to the point where we apply the physics. If you'd like more information, please talk to your instructor. But after we apply conservation of energy, we're going to end up with a model equation where 1/2 the mass of the cart times the speed squared is equal to 1/2 times the spring constant times the displacement squared. And from here, I'll be able to simplify the equation a little bit. And now the next step of the linearization process is to identify what variable we are going to change and which variable we are going to measure. In this experiment, I am going to change the mass of the cart. I'm going to add these additional masses to the cart and take a new speed measurement with each one. So my independent variable, what I'm going to change is going to be the mass. In my dependent variable, what I anticipate to change as a result of my independent variable changing is going to be the speed of the cart, the maximum speed of the cart. Now, this next step is the most important step when it comes to the linearization process. We need to get our model equation in the form of y equals mx plus b, where x is the independent variable and y is the dependent variable, or a function of those variables specifically. So in this case, I'm going to rearrange my equation so that the speed is isolated on the left-hand side and that my mass of the cart is on the right-hand side. I went ahead and I put in a few extra details into this equation as I was writing it. And I did that, I added the parentheses for one, so that my independent variable lined up with x in the linear expression. That is, I'm going to plot the function of my independent variable on the x-axis. I also added this plus 0 because that is the y offset. My model equation doesn't have some constant offset that's going to be present, so I just set it equal to 0, and this isn't related to b. The next step is to identify what is the x variable, or what is going to be plotted on my x-axis as a result of doing this linearization process. So I'm going to identify the independent quantity. Now, this independent quantity is going to be a function of the independent variable. In the case of this experiment, the function of my independent variable that I'm going to plot on the x-axis is 1 over mass. And now my dependent quantity is going to be a function of my dependent variable. So it's going to be a function of the maximum speed. In this experiment, it is going to be the speed squared. Now I get these by looking at the equation that is in step 4. So I have to look at this equation and I say whatever was the x variable in my linear expression now becomes the independent quantity, and whatever was isolated on the left-hand side is my dependent quantity. So now that I'm at this point in the linearization process, I can go ahead and identify specifically what is my objective, and then what are variables within the experiment that don't change. In this experiment, we're trying to find the spring constant of our spring. So the objective is going to be the spring constant, K, and we have a control variable in this experiment. We know we have a control variable because there are things in this experiment that don't change. We measure them once, and we use that measurement throughout the rest of the experiment. Another way to know that we have a control variable is when we look at this portion of my linearized expression, I have additional variables other than the objective. In this case, I have the displacement of the spring squared, or x squared. So I'm going to measure the amount that the spring is displaced once. I'm going to assess this uncertainty once, and then I'm going to use that as a control variable through the uncertainty propagation process. Now on to step 7 is probably the most challenging thing to understand about the linearization process. So I'll make sure to describe it as specifically as I can. When we take our independent quantity and our dependent quantity and we plot them against each other, we have our independent quantity on the x-axis and our dependent quantity on the y-axis. We expect that our data points are going to give us a linear relationship. The reason why that we expect that is because when we look at our linearized expression, the variables that are in front of the independent quantity are constants. The spring constant doesn't change throughout the experiment, and the spring displacement doesn't change throughout the experiment. So we expect those values, when multiplied together, to always be a specific number. And those are represented in the form of the slope of this data. And that's where we get from step 7, is we say that the slope of our linear expression is equal to everything in our equation that is in front of the independent quantity. And the last step of the linearization process that we're going to do on this sheet is we're going to rearrange this expression so that we solve for our objective. And after we collect all of our data and we do linear regression analysis, we'll be able to use this expression to propagate the uncertainty within our experiment. So as I look at the various measurements that I need to take through the course of this experiment, I want to capture how I'm going to conduct those measurements, and I also want to talk about and justify the uncertainty that I'm going to make with those measurements. So the first one is I'm going to be measuring the mass of the cart, and that's going to be my variable m is going to have units of kilograms. Now this is what I'm actually going to be changing, so this is going to be shown in my table, and I'm using a digital scale. The measurement procedures is I'm going to ensure that my scale is zeroed out. And then I'm going to take my cart and any additional mass that I may be including, I'm going to put them on the scale so they're all being measured at once. And so I would now conduct my trial. I would use these two masses and I would release the spring so the cart goes down the track. And if I were to take another trial, I would take another mass and I'd also add that to the scale and I would record the value there. As far as the uncertainty for this measurement goes, the manufacturer provides a specification for the scale. Everything that I'm placing on the scale is within the confines of it. There's nothing additional interesting going on, and so ultimately it's going to be the quality of the measuring device. The next measurement that I'm going to be taking throughout the course of the experiment is the maximum speed of the cart. And to do this, I'm going to be using the sensor, the position sensor within the Pasco Smart Cart and Pasco Capstone. My wireless cart has the ability to transmit its velocity to my computer. So I'm going to set up Pasco Capstone to do just that. So you can see in Pasco Capstone, I have my smart cart, the blue smart cart. I am using its position sensor, and on my plot, I have the velocity plotted as a function of time. Now mine is set up so it doesn't start measuring until the cart is moving. You can press record and then have the cart go, but you'll just have some lead-in time. That's perfectly fine. To get the maximum speed after the spring is released, I'll just go ahead and press record. And now the Pasco Capstone is waiting for my cart to move, so I'm going to release the spring. Stop the cart, stop the recording. All right, and now on Pasco Capstone, I can pick off the maximum value. And for this trial, I would say that I have a maximum speed of 1.271 meters per second. For the uncertainty associated with this measurement, I can't guarantee that I'm going to get the absolute maximum value because of the rate at which the data is being logged. I'm going to say it's the conditions under which the measurement is being made. Now, certainly there are other contributions to this, such as the manufacturer specifications for the cart, for the way in which we release it, and all of those do play in. I'm just trying to identify the largest contributor so that I can justify it, so that if you were to reconduct this experiment, that maybe you could change this one thing in order to get better results. So by the conditions under which the measurement is being taken, because I'm using a low data recording rate, I think that it's possible that I miss the maximum condition or the maximum speed. And then also because as I press this button, I may absorb some of the energy through friction, either using my finger or the metal rod. So for these reasons, I took a number of measurements. I found that they kept on consistently going within a window of about plus or minus 0.05 meters per second. The final measurement that we need to make is for our control variable, which is the spring displacement. That is x with units of meters. So this is the actual displacement from the relaxed position to the fully compressed position. And we're going to be using a tape measure in order to take that measurement. So the first thing I'll do is I'll measure the spring in the fully released position, and I'll use my tape measure from a known surface, which is the cart itself, and that's going to measure at 5.0 centimeters. And then I'll compress my spring and I'll find the difference. So now the tape measure is showing me 0.6 centimeters. So when I take the difference between those, I'm going to say that my spring displacement, or x, is equal to 4.4 centimeters. Now that is the magnitude of the measurement. I still need to identify the uncertainty of the measurement. This tape measure has tick marks down to 1 millimeter. And maybe if I was just measuring the spring in the relaxed position, I'd be able to justify, something smaller than that. But because I'm taking the difference between two measurements, I'm going to justify my uncertainty as being plus or minus 1 millimeter. I'm going to say that's because it's the conditions under which the measurement's being made, or maybe even the nature of the quantity being measured. I have to justify it, and I would make sure to communicate that through my lab worksheet. And in this case, I will write that as the nature of the quantity being measured, because I have to take two measurements and take into account both of those. I'm going to say that my confidence interval for this measurement, for the spring displacement, is 4.4 plus or minus 0.1 centimeters. When I say it's a confidence interval, I am confident that if you take that measurement with this cart, that you would get a measurement within that range. I am confident enough that I'd be willing to stake my grade on that confidence interval. Are you willing to stake your grade on your confidence interval? I said for this measurement, my confidence interval was 4.4 plus or minus 0.1. Now that was in centimeters, so this is going to be times 10 to the negative 2 meters. The relative uncertainty associated with this is a calculation that is 0.1 divided by 4.4 and is 2.3%. And the uncertainty is, or my justification of the uncertainty for this is going to be the nature of the quantity being measured. Since I have to take two separate measurements and combine them, ultimately I can't really get much finer than the tick marks on the measuring tape. Maybe I can find a better tool that would allow me to do it within a single measurement, but ultimately because I have to take two measurements, the nature of that quantity being measured is going to be the limiting factor. So those are the three measurements that we're going to take during the conduct of this experiment. The next thing I want to do before I take any data is I want to prepare some type of spreadsheet in order to plot the data as I go. That way, while I'm in the lab, if I don't get results that make sense, I can assess it as I go along. Now, I could record everything by hand and do it later on, but it's just as easy if I've already done the linearization process to build an Excel spreadsheet that allows me to do this in real time. This is for linearized experiments. This is kind of just a form in which you could follow, where you have the independent variable, you have the dependent variable, the independent quantity, and the dependent quantity. We've identified that our independent variable is going to be the mass of the cart and the additional masses as we go forward with the experiment. Our dependent variable, what we're actually measuring changes in, is going to be the speed of the cart after the spring is released. The independent quantity, again from the linearization, is going to be 1 divided by mass. This is what's going to be plotted on our x-axis. And then there's uncertainty associated with the actual mass, or the inverse of the mass. So These are reference cells, which is why you see divide by 0 right now. I'm saying I want you to, 1 divided by each trial, and then the uncertainty associated with 1 divided by mass is going to be the magnitude multiplied by the relative uncertainty. This falls out by taking the partial derivative of the independent quantity. You should ask your instructor if that doesn't make sense. For the dependent quantity, we're taking the speed squared. Again, these cells are referenced so that as I provide data, they're going to populate all the way down. And then the absolute uncertainty associated with speed squared, or the absolute uncertainty of my dependent quantity, again, this falls out by taking the partial derivative. It's going to be 2 times the magnitude times the relative uncertainty associated with the dependent variable. And what I want to do is I want to go ahead and produce a scatter plot. As I'm collecting the data, I want to display it in real time, so I'm going to select the data. I know there's a window you can't see, but I'm going to choose my X values to be my independent quantity and my Y values to be my dependent quantity. And then for my chart title, we're using this chart to determine the spring constant. That's going to be K. We're using plus result. Also on my chart, I want to have axis titles. On my x-axis, I'm plotting inverse mass with units of kilograms to the -1. And then on my y-axis, I'm plotting speed squared with units of meters per second, quantity squared. All right, so now as I go ahead and take data, the chart is going to populate with the independent and dependent quantities. For my first measurement, the mass is going to be recorded at 246 grams, or 0.2460 kilograms. And the absolute uncertainty associated with my scale is going to be constant throughout the entire experiment. So I'm going to go ahead and fill that all the way down now. And then as discussed, we already said the absolute uncertainty associated with the max velocity is also going to be 0.5 meters per second. So I'm going to copy that all the way down. So now for my first trial of no additional masses on the cart, let's go ahead and take our first measurement. Press record, and then get the maximum speed. The maximum speed is 1.24. So I go ahead and put that in here. And because I have my Excel spreadsheet built before I come into the lab, the data is plotted, and as I continue to take measurements, if I don't see a linear trend, then I know that something is wrong with my experiment. So I'm going to go ahead, I'm going to take the remaining 6 data points, and we'll build the sheet as we go. So now we've gone through, we've collected all of our data. We have 7 data points in total. So then it looks like our data fits a linear trend, which is good. So we're going to move forward with this data. So the first thing I want to do to improve this plot is I want to go ahead and add a trend line. So I'm going to right click on one of the data points and click Add Trend Line. On the menu that pops up, I want to display the equation on the chart and select display R squared value on the chart. And I'll go ahead and I'll move this around a little bit so that it's a little bit easier to read. So now the trend line itself has a slope, and I'm going to use the value of that slope to determine the spring constant. And then also we get an R squared value associated with this trend line. And that R squared value isn't necessarily telling us the uncertainty with the measurement or our measurements. What it's telling us is that with the value near 1, the data that we collected fits the model that we said that it would. So we used conservation of energy. We built out a model where we had the inverse mass plotted on the x-axis and we had the speed squared plotted on the y-axis. And we said that it was going to have some constant value that scales those measurements in a linear fashion. And as we plot the data, sure enough, that's what is represented, and that's why the r-squared value is very, very near 1. Another thing that we need to do to improve our plot is we need to add error bars. So I'm going to click on the extra menu, and now the error bars that Excel provides by default aren't associated with anything to do with the data we collected. So what we need to do is we need to click on the error bar itself. So I'm going to click on the independent quantity error bars. I'm going to right click and say format error bars. When I scroll down, I want to choose a custom range. I'm going to specify the value. Now these are all on the x-axis, or my independent quantity. I'm going to choose the positive error value to be the absolute uncertainty of my independent quantity. And I'll choose the negative to be the exact same values. And this will be the plus and minus values for my error bars. And then I'll go ahead and click on one of the error bars in the y direction. I'll do the same thing, but these will be the error bars associated with my dependent quantities absolute uncertainty. Negative value also being the same numbers. And I'll close this menu so that we can see. All right, so the error bars now reflect the uncertainty associated with my independent and dependent quantities. Those error bars don't provide any value to the slope or to the uncertainty in the slope that we're about to calculate. The uncertainty in the slope comes from linear regression. In order to get that, you need to install the data analysis tool pack. So I have that completed on my computer already. So under the data ribbon, I choose data analysis. I'm going to scroll down to the regression. And I know there's a menu that you can't see on my screen, but I'm going to choose the Y range to be the dependent quantity, and I'm going to choose the X range to be the independent quantity. And then I'm going to choose my output range to be somewhere on this sheet so that we can see where it populates. And I press OK. And now I get all kinds of information from the linear regression analysis that Excel just conducted. And what we really care about from this linear regression analysis is these two values right here. This is the slope. This value should very closely match what the trend line slope is. If it doesn't, that means that you made a mistake when you're going through the menus for the linear regression analysis. And then we have the standard error for the slope. This is the absolute uncertainty associated with our slope. So we're going to go ahead and we're going to add these to the plot just as it's specified in the SLAM. And that is slope is equal to 0.373. I'm going to add a plus or minus symbol. And my absolute uncertainty is 0.009. Okay, and now I need to figure out what the units are. And the way in which I do that is I say, okay, well, rise over run. So rise over run is going to be meters squared times kilograms divided by seconds squared. And I'll move this little box so it's nicely formatted. And if I need to do anything else to clean up the plot, I'd certainly do that. But this meets the standards for your lab submissions. And now that I have the absolute uncertainty, I have the slope in this absolute uncertainty, I can go ahead and move forward with the uncertainty propagation and calculating the actual spring constant itself. Okay, so now that we've collected all the data for our experiment, we've already measured the control variable or the spring displacement for each of our trials. We've gone through and we've varied the mass of our cart and then measured the resulting speed as we made those changes. We plotted those and we conducted linear regression analysis, and we've got to the part now where we can actually calculate the spring constant, but then also we can go a step further and we can calculate the absolute uncertainty associated with our experimental result. In front of me I have my error propagation table that you can find on the course website. And in this table, I'm going to start off by listing off my objective quantity, which is the spring constant. that is identified with the variable K, and it has units of newtons per meter. From my linearization table, I recall that my objective formula was that K is equal to the slope divided by the spring displacement squared. Okay, so now as I go through this table, I need to identify everything that is in this expression, and I need to identify its value and the absolute uncertainty associated with it. So I'll start off with the slope, and then I also have the spring displacement x. The measured value for my slope from the linear regression analysis was 0.373 with units of meters squared kilograms per second, and it had absolute uncertainty of 0.009 meters squared kilograms per second. And then the spring displacement had a value of 4.4 centimeters. I would like for that to be in meters so that I have everything in SI units. So that's 0.044 meters. And I said the absolute uncertainty with that measurement is going to be 0.001 meters. And now I need to use a calculator in order to identify the relative uncertainty of these two values. So 0.1. The relative uncertainty of my spring displacement is going to be 2.2% or 2.3%. And then the relative uncertainty of my slope is also very near 2% at 2.4%. I don't have any other variables in my objective formula, so I have everything in my table I need to move down to calculating the objective magnitude. I'm solving for K. And I get a value of about 193 newtons per meter. Now I list off probably more sig figs than I actually need, but I won't know exactly until I conduct the error propagation, the uncertainty propagation of what my confidence interval, what order of magnitude I'll actually have. So I list off a reasonable number and I'll get back to it. So the next step is to do the actual uncertainty propagation using the intermediate method or using the method of partial derivatives. They're one and the same, just different names for the same thing. And the expression for that is going to be the absolute uncertainty in my spring constant. I'm going to sum in quadrature the contribution of each of those individual measurements. We have another video that talks about why this is the case. I'll be sure to put a link in the description below. Okay, so I went through all the steps of doing the uncertainty propagation. I started with my base equation where I take the partial derivative of my objective with respect to each of the variables that are used to calculate it, and I multiply those by the absolute uncertainty of that variable. And so if you go back to the other video, this is kind of like looking at how each dimension of that block contributes to the uncertainty, the overall uncertainty with the spring constant. Over here, I went ahead and I took the partial derivatives of my spring constant, the calculation for my spring constant, and then I took those and I substituted in my values into this expression. And then I listed out, I calculated this value and I reported it here, and I calculated this value and reported it here. And I did this so that I can assess which measurement or which value within my experiment contributed the most to the uncertainty of my experiment. And because the contribution to the overall uncertainty from the slope is significantly larger than the overall contribution of uncertainty from the displacement, I know that when I need to change something on my experiment, I should change the measurements that I took to get the value of the slope. And then finally, I go ahead and I take this value into my confidence interval, and then I take this value into this confidence interval, and this should be newtons per meter. Don't forget units. The absolute uncertainty is always only ever 1 sig fig, so I'm going to round up to 5 newton meters. I need to reduce the number of sig figures shown in this value so that it matches the order of magnitude of my absolute uncertainty. And so in the end, I end up with a confidence interval of 193 plus or minus 5 newton meters. Now I'll go ahead and move forward into the Numberline analysis, where I compare this value to some known value or some accepted value for the spring. And I'll probably have to go to the manufacturer specifications to get a number for that for my passcode card. All right, so now that we've conducted our experiment and we've gone through and we've identified or we calculated the objective quantity of the spring constant, and we went ahead and we propagated the uncertainties associated with the experiment, we can finally go through the Numberline analysis process, where we compare our results to what we expected to get. Or a spring within this cart that has an accepted value or a manufacturer's provided specifications of 200 plus or minus 20 newtons per meter. And so now I'm going to compare my experimental results to what the manufacturer told me I should have in this cart. And to do that, I'm going to use a number line. You can find a blank one of these on the course website as well. And on this number line, we're going to be providing the spring constant. So when I look at the ranges in which I'm going to be doing this number line, I see that my lower end is probably going to be around 180, and my upper bound is going to be about 220. My accepted value spans this entire region. And my experimental value falls slightly to the left. And from there, I now have both my accepted and my experimental values, so I can compare the overlap of the confidence intervals. And because these two confidence intervals overlap, I'm going to say that I have some form of random error within my experiment. If they didn't overlap, then I would say that I have systematic error, meaning that there was something wrong with my procedures, or something wrong with my assumptions, or something wrong with my model that I provided to begin with. But because the error bars overlap, I have random error instead. So that means that as I was going through the process of the experiment, there were small changes within the experiment that I couldn't necessarily control, or maybe one of my tools had a limiting absolute uncertainty for each of the measurements. But I would need to identify which one contributed the most. And because if we go back to the uncertainty propagation, we could see that the uncertainty in the slope accounted for nearly all of the uncertainty in my confidence interval. I know that I need to go back and I need to evaluate the way in which I measured the speed and the mass. And since the mass is given to us pretty precisely with half a gram, I'm sure that the scale is pretty consistent. I probably want to go back and see if we can clean up the way in which we measure the speed. Maybe I can get a device that gives us a better resolution to get a more consistent measurement as we go through the trials. So with that, I would want to say that the dominant form of experimental error, I only have two choices, random or systematic, and in this case is going to be random. And then my conclusion is, because I have random error, I need to look back to see what contributed the most to the overall uncertainty within my objective quantity. I see that the slope, the absolute uncertainty in the slope is what contributed the most to the overall uncertainty in my spring constant. And as a result, I would recommend The reason why I would recommend we revisit the way in which the speed is being measured is because I think my scale is going to be very consistent, but I think that there's factors within the experiment that could change the way in which the speed is being measured. Maybe the spring plunger itself wasn't in contact with my rail every single time, and that contributed to the random error and the amount of distance that it would decompress before it actually came in contact and started exchanging energy.